Okay. Okay, so welcome, good afternoon, everyone, and welcome to this webinar where today we'll be presenting some work we've done on a project which was funded from the Race for 2030 CRC, as well as some other industry partners who are members of the CRC. My name is Frank Bruno. I'm from the University of South Australia. So I'm a research professor in mechanical engineering and also hold the position of South Australian Chair in Energy here. So Ming, are you going to give me control?
Sure.
I'll start off by just providing, going through the agenda today for the presentation and introducing some of the speakers who'll be presenting. So I'm starting off with an introduction to some of the speakers presenting today. Then Tracy Colley will be talking a bit about Race for 2030 and in particular the B1 business theme. Mark Haig from Outdoor Transport Engineering will be providing the industry perspective of the problem and challenges. I'll then be talking about, give it a brief summary of the project, how it came about and the problems and some of the work we've done. Ming Lu will provide some details on the techno-economic analysis we did of different concepts. Sohaila Riyah will talk about some modelling work she's done with different concepts. We have Peter Pudney, who'll be talking about charging patterns. And then we'll just hold off all the questions till the end. We'll have a session at the end if anyone has any questions, and we'll provide answers as required. So first of all, I'd like to acknowledge our partners for this project, the Race for 2030 CRC, the University of South Australia, Outdoor Transport Engineering, Symbol, and the South Australian Government Department of Energy and Mining. So I now hand over to Tracy to talk a bit about the Race for 2030 CRC.
Great, thanks, Frank. Next. Yeah. So this is just a brief introduction to Race for 2030. It's a CRC that started about 2.5 years ago, and the name is basically an acronym for Reliable, Affordable, Clean Energy Future. So that's really the aim of Race. And if it was started today, it'd probably be called something like Decarbonising Australia. But instead, it's about focusing on reliable, affordable, clean energy for 2030. We are a cooperative research centre, so it means that we need to engage with industry and ensure that the projects that we support respond to a need in industry. And our main objectives of the CSC are about saving energy costs, reducing carbon emissions, but particularly also being customer focused. So that relates to us being an industry CSC, us needing to sponsor work that is really integral to industrial and external partners. Next. So this really is at the start of the CRC. This was the projection that was made about what we wanted to achieve with the CRC, both for the life of the CRC, which is to 2030, but also beyond the life of the CRC to 2050, given that a number of the projects that we are looking at, like this project, rely on market uptake, and that won't stop in 2030. Hopefully that will continue, and so that the amount of greenhouse and energy savings and cost savings will continue to accrue to industry partners beyond the life of the CRC. Next. There are 4 research programs in Race for 2030. This one was sponsored under was Race for Business. We also have Race for Homes, Race for Networks, and Race for Everyone. And within Race for Business, there are 5 themes. Next. And so really what our CRC is all about is linking together everyone who has an interest in reducing greenhouse emissions cost effectively. So that means we link between not just research organisations like UniSA, but also industry partners like Aldrin in this instance, government like the Government of South Australia, but in various other projects in other themes, we also have network businesses, technology providers as well. So next. So for Race for Business, as I previously said, there's 5 themes. This project was supported through the theme 1, which is transforming energy productivity through value chains. For each of the 5 themes, an opportunity assessment was done in the early stages of the CRC. That was a very wide-ranging, comprehensive assessment of what the opportunities were for projects relating to these different themes. And for the first theme, the food value chain was one of the sectors that was identified as having a lot of potential for transforming energy productivity by looking at the value chain. And that's how this project came about. Next. That's it for me, I think. That's just my email and phone number. We're always interested in working with companies who have a need for research. So please feel free to make contact. Thank you.
Thank you, Tracy. And I believe, Mark, you're next.
Thank you, Frank, and good afternoon to everybody. My name is Mark Haig, and I'm the Managing Director of Aldom Transport Engineering. We've been manufacturing transport bodies for nearly 50 years all over Australia. We specialise in refrigerated transport bodies from last mile, as well, the one in the photo there, right up to 16 pallet rigids, and to carry all types of foodstuffs. My interest in electric vehicles and specialty trucks has become my focus over the last few years, and having built different types of bodies carrying all types of goods, I realised that electric truck bodies need to be light and efficient for carrying the perishables and the foodstuffs, especially obviously the refrigerated and frozen food groups. The challenges we've got is obviously the range limitation because of the extra weight of the batteries and the motors and what have you in the vehicles. And of course, the main thing is some of the bodies on the refrigerated bodies you see running around now on a rigid, let's say even a 10 palleter, 14 palleter can weigh up to 4 or 5 tons. So I knew this was going to be a problem with electric vehicles, having owned electric vehicle myself, and also just reading all about them. I knew we had to come up with a lightweight situation, light body. Millions of dollars, it's probably more like billions, but I thought that might sound a bit of an exaggeration. Certainly millions of dollars of food's wasted due to the variables in the temperature controlled transport with the high running costs to maintain the food at chilled and frozen temperatures. The noise pollution of the trucks on the motors and the auxiliary diesel motors as well is unacceptable. A lot of trucks now are unloading in the streets and shopping centres, and this is becoming more and more apparent, and we seem to be getting more and more food vehicles on the road, as we know, with the deliveries of food being delivered to homes. I've mentioned the pollution from the diesel and petrol motors to run the refrigerated units is also not sustainable. In that photo there, that's a Thermo King unit that's got a diesel motor in there and also electric standby, but that has to run the entire time the truck is parked. Also, the smaller trucks have to run their motor the whole time. So they're pulled up in a outside the front of your house, and they technically should be left on to keep the refrigeration running. Not to mention too that the drivers health, and so his own health of the driver has also got to be considered because with these fumes. Aldom joined Race for 2030 to design and build a body to enhance the PCM phase changing material, also known as Eutectics, that will be created by UniSA and its partners to deliver perishables and frozen foods during the delivery process in perfect condition with consistent and an even distribution of thermal efficiency throughout the body, which is very important. That's where they were getting a lot of the wastage and a lot of foods not being delivered in the right state. The PCM system and refrigeration unit will ensure the maintenance of the temperature conditions to meet the HACCP compliance. The design of the body will have thermodynamic performance and provide multi-temperature zones for frozen, chilled, and ambient isothermal requirements. The weight of the body will be reduced as the refrigeration unit can be deleted from the truck's chassis. And with a remote refrigeration unit back at base, you can charge the PCM and enhance the driving range of the vehicle, not carrying around the excess weight. Battery demand, as we know, will become paramount, and with all the energy used in off-peak times to charge the PCM system so we can take the pressure off the supply grid is a huge benefit. And we can realistically and consistently deliver the foodstuffs to the manufacturers and the processors' expectations and requirements. Some of the refrigeration weights too, I'd like to mention, on the smaller trucks can weigh up to 200 kilos, 250, and in the larger trucks, those weights can be up to 450 kilos or more for the diesel electric units. A further development that Aldom and UniSA are working on is a PCM cartridge that can be removed and replaced to provide a 24-hour or double shift application in the case of some of the food companies delivering the food around to the streets. So the vehicle is never off the road. The vehicle will also incorporate a swap-go battery to handle the double shift requirement to power the truck's electric motors. So you could start a shift at 6 in the morning, come in at 12, 12:30, whatever it is, change over the actual cartridge for the PCM, and you could change over the battery, and then the battery could do a second shift or even a third shift in some cases. Also too, which we haven't touched here, but I'd just like to mention it, hot food is also another phase of design, which I've had a little bit of experience in that already, but UniSA, we can also be able to do hot food or deliver pizzas or warm food or keep food hot. So we'll watch this space. We're working on that one. Our ultimate game, in summary, is to create an efficient, lightweight, low maintenance body with consistent and evenly distributed thermal efficiency that will deliver foodstuffs safely and economically to achieve the 2050 net zero target. Thank you.
All right, thank you, Mark. Okay, so I'll be presenting next, and so I'm just giving a project overview. So I'll be talking about, why are we looking at refrigeration in refrigerated transport? What are the problems? What solutions are other people providing? What's our solution, and what work are we working on? So first of all, why is refrigeration important in the food supply chain? Well, there's more than 23 million tonnes of foodstuffs in 2018, worth $42 billion that passed through the Australian cold chain. I provided a reference there, and I just want to say that for the rest of my presentation, I haven't actually put references because all these figures come from multiple references. You can find them in the actual report. The report is available on the Race for 2030 website, so you'll be able to read up on all the work we're presenting today, as well as look at all the references where all our figures come from. But refrigeration, as Mark pointed out, is important to maintain quality and freshness of the perishable goods. And obviously transport's crucial for the production, processing, distributing and retailing. Transport represents 60% of the total cost in the cold chain logistics. And yes, obviously we have to reduce the food waste and loss with better refrigeration practices. Next. The conventional refrigeration system in transport is similar to the refrigeration system is similar to the household refrigerator in terms it has the evaporator, condenser, compressor, expansion valve. That component is all the same. However, what drives the compressor is not an electric motor, but it's a diesel-powered internal combustion engine. That's conventionally what drives the refrigeration system. The diesel engine, a lot of that energy goes out to heat, to ambient, so we waste a lot of energy, and a small amount goes as kinetic energy into the compressor. So overall, the efficiency is reduced and not as high as what it could be when using a diesel engine. The typical COPs, which is that's a coefficient of performance, or the amount of cooling we get divided by the energy input. With the systems that a lot of the systems on the road, it's around 0.5 that are refrigerating at minus 20 degrees, which means half of the energy, that electrical energy, is being generated as cooling. With the newer systems, that might be approaching 1, so it might be a 1-to-1 ratio. And if we're cooling it around the 0 to 4 degree mark, then we probably have a coefficient performance of 1.5. Having an electric motor would increase those figures significantly. Also, if we were able to do the refrigeration off the vehicle, we could also increase it, because on the vehicle we have limited space for the components of the heat exchangers, so that limits our capability to maximize the efficiency. Also, the common refrigerants, the R134A, R404A, R4117B, they're actually being phased out. So we need to consider that if we're going to decarbonise refrigerated transport. Next. Some facts about the diesel-driven refrigeration in transport. Well, they use around 1.8 to 6 litres per hour. So a lot of the diesel trucks, they actually have their own diesel engine driving the refrigeration system, as well as another diesel engine driving the truck. And then there's also the ones that they take some of the energy from the diesel engine of the truck to power the refrigeration system. So there's two types, but they use around 1.8 to 6 litres per hour, and it represents around 5% of the total diesel energy consumption in Australia, which is around 70 to 90 million litres a year. If we look at what that equates to cost at $2 a litre, that's around 140 to 180 million dollars per litre per year. And as far as emissions is concerned, that's 189 to 243 kilotons of CO2 equivalent Scope 1 emissions. So all these figures are presented in the report, and the references and how we arrived at these figures is all explained. Next. So now I'll be talking about some of the types of refrigeration systems out there for vehicles. And the first one is a cryogenic refrigeration. So that uses either liquid nitrogen or liquid carbon dioxide as the energy source. So when the liquid gas turns into a gas, during that process, it actually creates cooling. So if you've got the liquid gas on the vehicle, then you're just expanding the gas, and so you've got the capability of a rapid pull down of temperature, very low noise, low energy consumption on the vehicle, and environmental impact. However, first of all, these systems are very expensive. That's the first thing. And the second thing is we need to think that we have to actually create the liquefied gas. So we need a lot of energy for that, and there's also a cost involved. Overall, there's a high cost of these systems, and the market penetration is about 1%. You can also get liquefied natural gas of these systems. So you still got a liquefied gas, but because you're using natural gas, once it's expanded, it actually goes into the engine to drive the vehicle. So those sorts of systems, and a handful of those systems are also driving on the road. Next. Now, eutectic refrigeration systems, which are systems that use phase change material, which is like an ice, but a phase change material, you can tailor the storage temperature at any temperature by using certain chemicals and ratios of chemicals. So these systems have been around for a long time. I'm familiar with trucks that were developed around 25 to 30 years ago. Those systems are designed for diesel-powered vehicles. They weren't thinking about electric vehicles at that time. So you can see here that those systems, they encapsulate the phase change material in plates and they locate them around the vehicle. So the advantage of the systems, there's no diesel usage because you charge this off the vehicle during the night. That's the idea. So there's also a reduction in energy costs and CO2 emission, and there's low maintenance and low noise. So there's a refrigeration system here that's electric driven, and you charge it by connecting it to the grid. That's the idea of this sort of system. Next. So the shortcomings of that system that has been developed and which hasn't changed over the last 25 years, the design, those plates are extremely heavy. There's a lot of scope to make those much lighter, which is important for electric vehicles. Also, the way that this system cools on the vehicle, it uses what's known as like passive cooling. So it means that the control of the heat transfer is very poor. The temperature inside is not uniform, so there's poor quality, temperature control. Also, the compatibility of the salts that are used in this case with the material, containment material, is probably the wrong choice. You can see there's corrosion, problems with the corrosion, and there is no local supplier in Australia. Next. Now, I'm not going to go through these in details, but there are a lot of types of systems that are being trialled or developed, or a small handful on the road. So there's ones that are electric. There are electric driven refrigeration systems that have been trialled. The first one there. Then there's also one with a battery that is charged whenever the truck is braking. Whenever the truck's braking, the kinetic energy in the wheels is basically converted to electrical energy, and that provides the energy to the refrigeration system. There is a hydrogen fuel cell powered vehicle and refrigeration system on trial on the road, and then there are small vans that use either the electric battery or the alternator of the diesel powered vehicle. So there are some vehicles on the, that have been trialled, developed. So we've explained more of these in the report. Next. Now, as I mentioned previously, we also need to think about refrigerants, because refrigerants have high global warming potential, the ones that are used at the moment. R452 is being considered to replace R404A. However, the global warming potential is still over 2,000. So to me, that's not the ultimate solution. We maybe should be thinking about natural refrigerants. R290, which is propane, typically used for a barbecue. The global warming potential is 3, and there is already several refrigeration systems for refrigerators using R290, as well as air conditioning systems, which is being used over the next 5 to 10 years with. Then there's also R744, which is carbon dioxide. Its global warming potential is 1, so there is scope to use a more environmentally friendly refrigerant in any new system being developed. Next. And I just wanted, this slide's just showing that the market for refrigerated transport, the number of refrigerated vehicles is increasing over the years. And also there's going to be a transition from diesel powered refrigerated vehicles to electric powered refrigerated vehicles. Next. So this slide shows the work packages in this phase 1 project of our long-term project. So the university in Oldham, we did a techno-economic analysis, and that will be presented by Ming later on in another presentation. We had Sahela particularly working on computer modelling of the different concepts of eutectic refrigeration systems. We had Peter Pudney working with alongside with Symbol and the South Australian government on the charging pattern control system. And Oldham particularly have been looking at the truck body and how lightweight materials can be used to help decarbonise the refrigerated transport sector. So after this project, the whole purpose of this project is to come up with a concept design, and the next project, which is about to commence, we'll be looking at building a prototype and trialling it. Next. And so some of the work that we did in this first phase also is that we looked at, we tried to develop some new phase change materials that are specifically tailored for the refrigerated transport sector. So some of the results are presented in the report. Next. And this last slide here really just shows that we focused on developing the phase change materials for cold temperatures at -18 degrees, as well as refrigeration temperatures between 0 and 4 degrees. And so that concludes my presentation. And so next we'll now go over to Ming, who will talk about the techno-economic analysis.
Hello, everyone. My name is Ming Liu. I'm a research fellow at the University of South Australia. So in this tech economic analysis, we have compared and evaluated 4 types of transport refrigeration systems. The first one is the diesel-powered vapor compression refrigeration, as Frank talked about in the beginning of his presentation. So this is the most common technology on the market. And the second one is the battery-powered vapor compression refrigeration. The third and the fourth are the eutectic refrigeration system, which employs the phase change material. And in the commercial system, the phase change material, the PCM, is encapsulated in the flat plate, and those plates are mounted underneath the roof and in the front of the refrigerated space. In this project, we're looking at a different design, so which means all the PCM are encapsulated in one box, and we located this box in the front of the refrigerated space. And this design is supposed to have a better and controllable temperature management. The Type 3 and Type 4 are different in how to charge the system. So the Type 4 is straightforward. We have a electric refrigeration unit on board of the vehicle. So whenever the PCM have molten, there is no stored energy and there is power, you can charge the PCM. And the third one is we need to have the facility in the warehouse. So the truck can be charged when it's back to the warehouse through a secondary heat transfer fluid. And Mark mentioned a swap and go system. So there is potentially we can leave the refrigeration unit in the warehouse too, and use a there is a type of connection. We can just use that to disconnect from the a PCM system. All the refrigeration systems are sized for a medium 2-compartment refrigerated vehicle. This type of vehicle was suggested by Oldham to target supermarket customers. And the vehicle can be used for delivering fresh and frozen food in Adelaide climate conditions. This table has the assumptions and the estimated values used in the analysis, including the COP, the cost, the weight of the refrigeration unit, and the cost and the property of the battery, and the property and the cost of the PCM, also the cost of diesel and electricity. So I'm not going to go through every numbers here. If you are interested in any specific assumption, we can come back later on. So now let's have a look at the refrigeration load for this truck. The peak load is 2,680 watt. And for this size of vehicle, Thermo King recommend to use its T590 diesel-powered refrigeration unit, which has a weight of 413 kilograms, and this is a specification for the unit. To size both the battery and the eutectic refrigeration system, we need to know the daily refrigeration energy before you next charging. So therefore, an hour-by-hour load calculation has been conducted. And the daily energy is 20.2 kilowatt hour. For the diesel powered system, it will consume 10.9 liters of diesel. To provide the same amount of energy, it needs 360 kilograms of PCM or 243 kilograms of battery. This is the analysis result. So we have calculate the capital cost of the refrigeration system, the operating cost per day, the cost of ownership over 10 years, and the weight of the system on the vehicle, and also the CO2 emission. So due to the high cost of battery, the battery powered system is the most expensive one. And the eutectic system is the cheapest, which is the current case. So the commercial product of the eutectic refrigerated truck, it is cheaper than the diesel truck. And for the cost of energy per day, I only considered the cost of the diesel and the electricity. There are some other costs. So for example, the maintenance, the repair, also insurance and personal training. I didn't include that, but different system will have different values. So the if we look at the cost of ownership, the eutectic system is the lowest, is below 20,000 over 10 years. And the battery powered system, even though the capital cost is high, but the operating cost is very low compared to the diesel system. So therefore, over 10 years, it is cheaper than the diesel powered refrigeration. And if we have a look at the weight, due to the high energy density of the modern battery, the battery system is the lightest. And the eutectic system having the PCM, this is heavier than the other two. And the CO2, the amount of the CO2 emission is calculated assuming both the battery and the eutectic system is charged by electricity grid from South Australia. The emission factor is 0.43. So I know in the other state and territory, they have a higher emission factors. But potentially those systems can be charged using renewable electricity, so that then the emission will be zero. The next few slides present the result from some key parameter analysis. The first one is the insulation R value. We have varied the value from 2 to 20. And the graph on the top presents the impact of the R value on the total refrigeration energy and the refrigeration load. And the bottom graph presents the impact of the R value on the weight of the battery system and the eutectic system. So you could see that the battery powered refrigeration, which is this green line, is the lowest in most of the studied case. But the eutectic system, type 3 system, when the R value increase, the weight reduced a lot, and at the end, it is comparable with the battery powered system. And the second parameter we have look at is the specific energy of battery. There are different types of battery as shown in the table. As it is well known, lithium-ion battery dominates the market. And based on this value range, we have selected 4 specific energy, which is low, medium, high, and very high. And this graph shows the weight of the eutectic refrigeration system, which is the horizontal line, and the weight of the battery-powered refrigeration system, which is this blue line. And it is found that when the specific energy of battery is greater than 150 watt-hour per kilogram, the battery-powered refrigeration system will be lighter than the eutectic refrigeration system. Another parameter we have looked at is the cost of the battery. So the cost of the battery has fallen significantly over the last decade. And until 2021, is the lowest at $141 per kilowatt hour. And at 2022, the price slightly increased, and now it is stabilized. It is predicted that the battery price will drop again from 2022. So in this analysis, we have selected 4 costs from 150 to $70 per kilowatt hour. And the cost of the battery-powered refrigeration system is plotted in this orange line. And the number here is the cost of the battery in Australian dollars, because all the other analysis has been done using Australian dollars. And we could see that this horizontal line is the cost of the eutectic system, tab 3 and tab 4. And even though if in the future the cost of the battery can drop to 70 kilowatt hour, $70 per kilowatt hour, which is less than half of the current price, the cost of the battery powered system will still be expensive than the eutectic system. So in conclusion, the eutectic refrigeration systems have the lowest capital cost, operating cost, energy consumption, and CO2 emissions. The battery-powered system is still the most expensive one, considering the future price drop. When the specific energy of battery is greater than 150 watt-hour kilogram, the battery-powered refrigeration system has the benefit of adding less weight to the vehicle compared to the eutectic refrigeration. So this energy density is very achievable with the modern battery. The improved insulation will result in smaller and lighter refrigeration system. The difference of the weight between the battery system and the eutectic refrigeration system becomes smaller with the increasing R value of the insulation material. So that's it. That's for my presentation. So I will hand over to Sohaila.
Good afternoon, everyone. My name is Sohaila Riahi. I'm a mechanical engineer, research associate at UniSA. I have experiences as a mechanical engineer. I have expertise in computational fluid dynamics, CFD, and finite element analysis. I use those tools for thermal design and structural design of energy conversion and energy storage systems. So for Aldom project, we started with exploring using the CFD analysis for exploring the commercially available system. In commercially available systems, as Frank mentioned before, the PCM is embedded, encapsulated in plates and is distributed along the top of the container and in the front wall. So it has its own advantages and disadvantages. So we used geometry. You can see at the right-hand side, geometry that we made, and we used the information from manufacturer regarding the number of embedded places and the kilogram of PCM they used in. So modeling that we explored the different length, we learned from the modeling results showed us that important parameters are the aspect ratio, the length of the container, the distributed system where the location of the PCM systems. And the fan. Fan, we learned that fan for the containers, smaller containers, for example, around 4 meters or less, it's not necessary. And because the convection heat transfer works because of the temperature differences and density differences. However, for longer containers, it is necessary because it is important to have a good circulation of air around the PCM heat transfer areas, and that results in a more uniform temperature that can keep the foods in better quality during the delivery time. Here we show some of the results. For example, the top two figure shows the velocity vectors and velocity distributions in the container. For example, we put a fan location at the front wall. You can see that is the higher density of the vectors around there, and how the air circulation versus the density of the vectors shows us, and the density and the velocity distribution. One of the interesting things from here we can see is that the air curtain at the back, when, for example, the door is open, we can model it in different way, and you see from the density of the vector at the back, if there is a good air curtain there that provides a barrier from the hot outdoor air entering the container. So the important parameter here is the fan, the outlet velocity, and pressure. You can play with those numbers and the mass flow rate, and then that shows you that which of them is optimal air circulation, uniform temperature, and good air curtain at the back. But the bottom two figures shows the temperature distribution and the heat flux, heat transfer. So this, for example, temperature profile inside and outside can show us that if there is any stagnation point, if there is any area that it's hot spot. And from the bottom right, you can see that the heat transfer from the plates that are closer to the fan is higher with the red light, red color, and the heat transfer from the plates that are further from the fan is lower. So this means non-uniform melting. So it's another point that is important is that with this modeling, we didn't have any pallets, any packages inside the container. Having them, the thermal load of them and the distribution of them and how they are located there, it is important because that might provide some sort of, as I mentioned, hot spot that we don't want. Having them modeling, including them in the modeling shows that which configuration of fan, location, velocity, and pressure provides the best air distribution and uniform temperature. Next, please. Looking at the commercially available system advantages and disadvantages, we thought about a few alternative designs, a few concept designs. Most of them are like centralized system, So centralized system have advantages compared to the distributed system. That is it's easier to access, is in one location. So everything from the maintenance point of view, or if you want to swap them, is much easier. And you have access to that site that you can access to them. With this sort of fan is required, no matter the length, because it's in one location and you need a good fan with optimum velocity and outlet velocity and pressure to bring the heat transfer to cover the whole area of the container. So here we sort of comparing the centralized system with the distributed system. Similarities are that the aspect ratio and the length, the fan location, velocity and pressure are important. The air curtain at the back is important, and also the inclusion of the packages and pallets. But important difference is that we have another important parameter that we can play with it, is the inside that package for PCM. The PCM encapsulated systems can be different. The orientation and the configuration can be different. So the parameters there are important. That's the heat transfer area arrangement inside that section gives us a more sort of parameters to work with. So, okay, from this analysis, we use the CFD from the comparing those advantages, disadvantages. We came to we selected one concept design that we did more modeling, further modeling to understand the mass flow and heat transfer. Here is the result of the modeling that we did for the selected concept design. Still, it is a centralized system with a specific arrangement of encapsulated PCM inside in that section. We are not going to show more detail of that inside of that, but again, the two figures at the left are the velocity vectors and velocity distribution. Interesting here, you can see that, for example, there is a bit deficiency from the vector densities at the right-hand side, at the left-hand side figure. You can see that there is a bit deficiency in air distribution closer to the back of the door if doors are open. So that's the strength of the CFD modeling, because you put a fan in a location with a specific outlet velocity and pressure, and you can see if provides a good air distribution, specifically at the back when door are open, there is a good coverage there as a barrier or not. So then you can change those parameters to get the best coverage that is desirable. Again, the two figures at right-hand side, they show the temperature profile and the heat flux. So it's different comparing to the distributed system. And again, the results provides us, is there in any deficiency? Is there in any hot spots that we have to deal with it? How the heat transfer from the centralized system is working, is more uniform or not? So we can play with those parameters, changing them. We can design the optimum system. Yeah, okay. I think I covered all of the information I wanted to mention about the centralized system. So the next step is having the pallets also inside the container. That is important. Having the thermal load from them as well, because here just we included the heat transfer between the inside and outside. Using the CFD modeling, but we need also use the finite element analysis. Here, the thermal load as mechanical load are not important, but because it is a moving body, there are mechanical load that we need to consider, and working with engineers from ALDOM, we can work out what are those mechanical loads and model them in finite element analysis, and make the structural design of that PCM section robust, and that is robust and appropriate for the moving body. So yeah, I think I covered what I wanted to mention. Thank you.
Okay, thanks, Suhaila. So Peter Pudney, you're next.
Yep. So I'll move through this pretty quickly. Next slide. We took a fairly broad view of the problem. How you best charge your or charge your cooling system depends a lot on the type of trucks you have, the pattern of use they have, when they're available for charging, and also the type of cooling system you've got, whether it's a battery electric system or a eutectic system. And it also depends a lot on the availability of electricity, how much capacity you've got to recharge, if you're using electricity to recharge, and the tariffs that you're paying for. So the kind of issues we identified were that if you've got a cooling system on the truck that's powered by batteries on the truck, then you can use the same sort of AC charging that's used for electric cars. And that's very inexpensive and can be installed at depots and at destinations, but charging is fairly slow. DC charging is a lot quicker, but it requires expensive dedicated chargers. And battery swap is also very fast, but it does require standardized batteries and handling equipment, and you have to have more batteries than you've got trucks so that you can be charging some while your trucks are out on the road. For the eutectic systems, if you've got onboard refrigeration, you don't need any special charging equipment. It can be done at depots and destinations, but it's fairly slow. If you're running off-board refrigeration, so this is where you cool a fluid that you then pump through the truck when the truck arrives back, that can be fairly slow, but you can pre-chill some of the cooling fluid. And then swappable cold packs are fairly fast to change, but it requires specialist handling equipment at the depots. Next slide. Yep. So the sort of cost issues are, there are many different tariffs around that at the moment. So there's about 100 different tariffs available in the Australian market. So flat tariffs where you pay a single rate for electricity really don't give you much incentive to schedule your charging, but these sorts of flat tariffs are becoming less common now. You might get a tariff that varies with the time of use, so you get cheaper prices during the middle of the day, particularly in South Australia, or overnight. They're fairly predictable. Real-time pricing, you can get access to the wholesale energy market where the price changes every 5 minutes, which is more difficult to predict, but can give you some significant savings. And critical peak pricing occurs when you get alerted in advance that there's going to be times where the price is going to be very high. And so you need to work around those. Many businesses have demand charging that depends on the greatest amount of demand they put on the grid during the month or even during the year. They're a bit tricky to work with, but you can work with those. And you may also have demand management incentives where you're paid to reduce your demand during periods of high demand on the grid. And then last slide, thanks. So if your truck schedules are predetermined, then designing an optimal charging schedule is fairly straightforward using standard mathematical optimization tools, but it does depend very much on your operation. So it depends on your electricity tariff if you want to minimize the cost of charging. It depends on when your renewable energy is available if you want to maximize the use of renewable energy. It depends on when your trucks, batteries, or eutectic systems are going to be available for charging. And it depends on the charging characteristics of whatever system you're using for cooling, whether you can charge it quickly or slowly. You may have constraints on the number of charging stations that are available at your depot. You typically have fewer charging stations than trucks, so you need to schedule those through. And you may have constraints on the amount of power you've got on site in order to simultaneously charge several trucks. So these are all problems that are very specific to the type of operation that you're running, and also the type of cooling system you've got in your truck. And we will be looking in detail for specific situations in the next phase of the project. And then the problem gets even more challenging if you're prepared to vary the way you run your truck schedules in order to get access to cheaper or cleaner charging. I think I'll leave it at that.
Okay, thanks, Peter. Okay, so I just want to mention that we actually started a little later today, and we've also gone a bit over time. So unfortunately, a lot of people that joined us earlier have had to move on to other meetings. I just want to mention, if anyone has any questions, feel free to ask us, send us an email or give us a phone call. We'll be happy to answer it. But if anyone does have a burning question now, please say so. Does anyone have a burning question they'd like to ask?